Yes, Thompson.
We have a question which maybe you'd settle for us.
Be glad to try.
Well, is it true that a plane will always warn you before it stalls?
Well, yes and no. That depends on what you call a warning. For instance, in a turn, the warning may be much less noticeable and the stall approach more rapidly. Also, you may have an entirely different set of warnings than you'd have in a wing level stall.
And why is the stalling speed in the turn higher?
Now, let's go back to the beginning. You know what angle of attack is?
Yes, sir. It's the difference between the direction your wing is pointed and the direction you're traveling. Now, in slow flight, for instance, you may be traveling a perfectly level course and yet have your wing pointed up like this. So here is your angle of attack, and in this case, it's a fairly large angle.
That's right. Now, do you know the relationship between lift and angle of attack?
Well, when you increase your angle of attack, you also increase your lift, don't you, sir?
That's right. A fairly oversimplified example of that is that if you put your hand out of the window of a moving car and tilt it up a little, the wind will try to make it go up. By tilting your hand, you're increasing its angle of attack. And the more you increase its angle of attack, up to a certain point, the more the wind tries to make it go up. In other words, the more lift it has. But in an airplane, the amount of lift you have depends not only on your angle of attack, but also on your airspeed. Cutting down on airspeed at any given angle of attack cuts down on lift. That's why when you go from cruising into slow flight, as you retard throttle, you ease the nose up. By increasing the angle of attack as the airspeed falls off, you keep lift constant and therefore do not lose altitude. With that in mind, let's see what really happens to the airplane when we do a wing level stall. As we lose airspeed, we keep easing the nose up, attempting to maintain altitude until one of two things happens. We finally reach the stalling angle of attack, which means the air is no longer flowing smoothly over the wings and stall. Or if we had simply held the plane at a high angle of attack, without easing the nose up so high as to exceed the stalling angle, the airspeed will drop off to a point where the plane starts to sink. The air would then strike the wings from this direction, and that causes us to exceed the stalling angle. The airspeed at which this happens in the wing level power-off stall is called the normal stalling speed. So when we say the normal stalling speed of a plane is 45 knots, we mean that it takes the maximum angle of attack plus at least 45 knots of airspeed to provide enough lift to support the weight of the plane. Now, we know that in straight and level flight, lift must be exactly equal to weight. Let us assume that we had a plane which weighed 3,000 pounds. Then it would take 3,000 pounds of lift to keep it flying straight and level. The force of lift always works perpendicular to the wings. So when we put the plane in a bank, it is the tilting of this force to one side which causes the plane to turn. Some of this lift is now diverted to start and keep the plane turning. The fact that the plane still wants to go straight ahead creates centrifugal force equal to the turning force. The actual weight of the plane plus centrifugal force results in what is sometimes referred to as apparent weight. It follows that lift and apparent weight must be equal. For example, in a 70-degree bank, apparent weight is about 3 times as great as in level flight. So we have to produce about 9,000 pounds of lift. This requires all the lift we can get from the maximum angle of attack, plus an airspeed of not less than 77 knots. In other words, 77 knots is the stalling speed in a 70-degree bank. As we decrease our bank, apparent weight decreases and the stalling speed drops, until in level flight we have apparent weight equal to actual weight and a stalling speed of 45 knots.
I didn't know there was that much to it.
Almost takes a course in aerodynamics to explain it. But it's built that every pilot should have if he values his neck. On the other hand, that alone won't keep you from stalling out. You can't see your angle of attack, but the feel of the airplane, the way it looks and sounds, will tell you as much about your angle of attack as you would know if you could see it. For instance, as you steepen your bank in a turn, the apparent weight of the plane increases, and the pilot also seems to get heavier. If you were to put a small bathroom scale on the seat of the plane and you sat on it instead of on your parachute pack, you'd find that in the air, in straight and level flight, your weight would be about the same as when the plane is sitting on the ground. But put the plane into a 50-degree bank, and you'll weigh half again as much as you did in straight and level flight. you're putting 1.5 G's on the airplane and on yourself as well. Then as you shallow the bank, the excess weight will decrease. Put the plane in a dive. As long as you follow the established course of the dive, your weight will be just about normal. Also, notice that you're flying at very low angle of attack. But pull out of the dive. The sharper your pull out, the more you'll weigh. Also, the sharper your pull out, the greater your angle of attack, and the nearer you are to the stalling angle. So that feeling of heaviness can tell you a lot about your angle of attack. The heavier you feel, the nearer you are to the stall. So we can put down that heavy feeling as a stall warning. It is present only in turns or pullouts and is a warning only for stalls at higher normal speeds. It does not apply to slow speed stalls. The other warnings for stalls at higher normal speed are excessive back pressure and vibration.
Sir, do you mean excessive back pressure on the stick?
That's right. Now, I don't want you to become too conscious of the controls of the plane. But before you stall out at high or normal speed in most airplanes, you'll find that you're pulling back at least fairly hard on the stick. The one exception to that, of course, is when you have the plane trimmed in an excessively nose-high attitude. Now let's compare these warnings with those we get before a stall at slow speeds. Instead of the heavy feeling, you'll get a sinking feeling before the stalls at slow speeds, or at least you'll feel a loss of buoyancy. There won't be the excessive back pressure on the stick that you would exert in high or normal speed stalls. Instead, the controls feel mushy. A primary trainer usually develops a sort of shudder before it stalls out at slow speeds. Also, the plane sounds wrong. But sometimes the stall develops so suddenly that unless the pilot is thoroughly alert, he won't have time to recognize the warnings. In a skid or a slip, for example, the stall occurs sooner and is more vicious. Here's why. In balanced flight, the air flows straight back across the wings from fore to aft. If you were to slice through one of the wings on a line following the flow of air, the cross-section would look like this. When you skid or slip, the air travels diagonally across the wing, and the cross-section following the flow of air would look like this. The air has to travel further to get across the skidded wing, resulting in a different type of low-pressure area which doesn't have as much lift. Likewise, since your nose is cocked off your flight path, you are cutting the lift on one wing more than the other. It is as though the airplane had one wing shorter than the other. Of course, until you've had a little more experience, you'll inevitably slip and skid a little. But beware of unbalanced flight at high angles of attack, that is, at slow speeds or in steep or even medium turns.
But, sir, when you use the wing-down method of drift correction, you're actually slipping, aren't you?
Yes, but the amount of slip isn't sufficient to be dangerous at gliding speed and straight flight. Later on, you'll learn to use the slip to boost altitude quickly, much steeper slips than you'd use for drift correction. But you'll learn the feel of that kind of a slip, and you'll learn to balance it in such a way that it becomes a perfectly safe maneuver. So the time to be on the lookout for stalls is when you're flying at a high angle of attack. In other words, when your speed is slow or when you feel heavy in a turn or a pullout. Also, beware of skids and slips.
Slow speed, when you feel heavy, and when you're skidding or slipping a turn, that's when stalls occur. Is that right, sir?
Exactly. And these are the stall warnings. If your angle of attack approaches your stalling angle slowly, you'll usually get lots of warning. The faster it approaches your stalling angle, the shorter will be the period of warning. Skidding and slipping will also shorten the warning period. The way to avoid stalls is to get plenty of stall practice at safe altitudes until your reaction to the stall warnings becomes instinctive, until you're highly sensitive to the conditions under which stalls may occur. It takes all the clues together, the entire sight, sound, and feel of the airplane to tell you what's happening or what's going to happen to the plane. With lots of that kind of practice, plus a thorough understanding of the dope I've tried to give you today, there's no reason why you should ever stall out when you're too low to do anything about it.